Introduction. Welcome to this video. Today, we're diving into how the radar equation and the detection process fit together, as shown in this block diagram. This will be a great recap of what we've learned about the radar equation and how the calculated signal-to-noise ratio, SNR, fits into the detection process. The main question we're addressing is there really a target, or is it just noise? The radar equation. First, let's review the radar equation. It connects several key factors. Radar parameters, this includes transmitter power, antenna gain, the directivity of the antenna, frequency of the radar, pulse width, waveform. All of these elements influence how strong the radar signal is relative to the noise. Target characteristics. The radar equation also depends on the target's cross-section, which is affected by the angle at which the radar hits the target, the frequency of the radar signal. This cross-section determines how much of the radar's energy is reflected back, and it can change based on the target's orientation and shape. For instance, a flat surface perpendicular to the radar will reflect more energy back than one at an angle. Range. The distance from the radar to the target is critical. The signal-to-noise ratio is proportional to 1 by our power 4, meaning the farther the target, the lower the SNR. Propagation medium. The environment the radar signal travels through also matters. Factors like rain and atmospheric conditions can attenuate the radar signal. These combined parameters give us the signal-to-noise ratio, SNR, which we usually aim to be around 20 or more for a good detection, about 13 dB. For some situations, a higher SNR may be necessary. The detection process. When we use radar, we're not just receiving a static signal. The noise fluctuates, creating what we know as static and radio signals. This is because noise is a random variable with Gaussian statistics. In other words, noise doesn't stay constant. It fluctuates around an average value. Similarly, targets also fluctuate. For most targets, except a sphere, the radar cross-section changes as the target moves. For example, an aircraft will have multiple scattering centers like the nose, wings, engines, and small changes in its position can change how much radar energy is reflected back. These fluctuations impact the detection process. The challenge is setting the detection threshold. Ideally, we want the target signal to be clearly separated from noise, but in reality, their distributions overlap. This creates a balance between probability of detection, PD, the likelihood that a threshold crossing is indeed caused by a target, probability of false alarm, PFA, the chance that we mistakenly detect noise as a target. In future videos, we'll dive deeper into this detection process, covering topics like target fluctuations, setting thresholds, and how to maximize detection while minimizing false alarms. Conclusion. If you found this overview helpful, make sure to subscribe for more detailed breakdowns on radar technology.